In this video, we're going to discuss something called the normal approximation to the binomial. So what do we mean by this? The idea is that we have a binomial random variable and we're trying to calculate probabilities for it, but it's going to turn out that it might be easier to use the normal random variable to approximate that probability. And in this section, we're going to learn how to do that. So let me give an example of why we might want to do such a thing. Let's suppose that we order 10,000 of some device, and there is a 0.001 chance that any device comes broken. And so what we'd like to do is we'd like to say, well, okay, well, maybe if we have like one or two broken things, we can still get by with the rest, but we don't want to place an order and have a whole bunch of them broken. So what's the chance that we have more than, let's say, 5 broken in our order? Maybe that's our cutoff before we're not happy with our shipment anymore. Well, we learned you can find the probability for a binomial variable for any specific value of k using this formula right here. However, if I want to find the probability that there's more than 5 broken devices, I would need to find the probability where there's 6 broken, and 7 broken, and 8 broken, and 9 broken, and so on, all the way up to 10,000. That would be an insane amount of work. Now, sometimes we could set it up to where we take the complement and then we just do 0, 1, 2, 3, 4, 5. That'd be a lot better. But complements don't always help that much. And so what they learned is that when you have large sample size, which is when this can be a problem, we can look at the binomial distribution and it's actually going to be very similar to a normal. So the idea is when n is large enough relative to these probabilities, p and 1 minus p, then the shape of the distribution, if you were to graph out the binomial random variable, and it is a discrete random variable for binomial, that if you do that, it's close to a normal distribution. Now, it can never be exactly the same as a normal distribution because binomial is discrete. It can either be 0 or 1 or 2 or 3 successes. You can't have 2.5 successes or 2.75 successes. That does not make any sense for a binomial random variable. Whereas for a normal random variable that is continuous, you could have an x value of whatever number you come up with, 2.89. That's perfectly valid in a normal random variable. So it's never going to be exactly the same. But the idea is if they're close enough, maybe we can use the normal distribution in order to get the answer. Now you might say, well, the normal distribution, that's something you also can't do by hand. So why would we do this? But at this point in time, when this method was developed, we had the table for normal distributions, and we could use the table pretty effectively. And so that's how this method was kind of developed. So we take our hard binomial problem, convert it to a normal problem, use our table, get our answer, and say that's approximately the right answer for the binomial problem. With that said, nowadays we can get a lot of these things done with our calculators without having to do an approximation. So this is a little bit outdated, but it's still useful to talk about here, and it's actually something that will come up in a later section as well. Now, this next question I asked is, when is this approximation going to be good enough? When is it going to work well? And that's actually not an easy question to answer, and there isn't necessarily even one correct answer to it. In fact, in all the time I've been teaching statistics, I have seen different books give different answers to when is this going to be a good enough approximation. The one we're going to go with nowadays in this class is that if you take the n, multiply it by the p, and then multiply the answer by 1 minus p, that the number you get here is at least 10. So if this is true, the normal approximation will work well. So you would take your numbers here. So in this case, we had an n of 10,000. My p was 0.001. If you take 1 minus that, you're going to get 0.999. And quickly pull out our calculator here and see what we get. 10,000 times 0.01 times 0.999. And I get 99.9, which is certainly at least 10. So it satisfies our condition. That means using the normal approximation will be a pretty good answer for this problem. Now, of course, when we're dealing with this section and we ask you to use a normal approximation, guess what? The n times p times 1 minus p is going to be at least 10. We're not going to ask you to actually use the approximation when that condition fails, because it would not be good enough for our class. However, we could ask you a question, instead of saying, perform the approximation, we could say, would the approximation work well in this case? And which means you have to check that little condition there. So before we can actually do this here, we need to talk about something called the continuity correction. This goes back to what I was saying earlier, that the binomial random variable is a discrete random variable, whereas the normal random variable is a continuous random variable. And so if I take x to be the binomial random variable and y to be the normal one, then if I take the probability that x is equal to, let's say 7 here, you'd get an answer. And you can get an answer. It's not going to be 0. It's going to be, c, n, 7, p to the 7, 1 minus p to the 7. Or not 7, n minus 7. All right, so that's not 0. However, for any normal variable, the chance that you are any one particular number is 0. Because the area under the graph, height times width, the width is 0 because you're at 1 point. It does not make any sense. You'd have 0 area there. So that's obviously not a very good approximation. So here's what we're going to do. We are going to imagine that you are going to take a box located around your value here. And so instead of just taking the exact area right above 7, we're going to take a box around it, and that's the area we're going to look for. And if I want each number to have its own box, and I want those boxes to not be overlapping, well, what's the natural point to cut off here? Would be at going half. So if you're between 6.5 and 7.5, that's the part that's around 7. And if you're between 7.5 and 8.5, that's the part around 8. So then what we're going to do is we're going to say the probability that x is equal to 7, that's approximately the probability of y is in between 6.5 and 7.5. So that's what you would do for a single number. Then what if you wanted to say, I want all the numbers that are less than or equal to 7? Then in terms of the normal variable, I want all the numbers less than 7.5, because I want everything that includes the 7 part and everything to the left. So the stopping part for that is 7.5. On the other hand, if I want the probability that x is less than 7, that means I do not want to include the 7 part. I want only things to the left of it, so I stop here at 6.5 to not include that. So every time you're converting from binomial into normal to do the approximation, and it should really be approximal, equal, not actually equals, but every time you're converting from binomial to normal, you're either going to add or subtract a 0.5, and that's going to be based off of whether you want to include that number or not. So you have to really try to figure out what you're looking for. In this case, less than or equal to 7 or less than 7. Do I include that number or not? And if I do, then I go ahead and add or subtract the 0.5. So here's a quick example. We have x is a binomial random variable. They tell us that n is 80 and p is 0.75. And I want to use the normal approximation to find an approximate value for x is greater than or equal to 62. So if you look at your picture here, I want everything that is greater than or equal to 62. I do want to include 62. So if I want the box that is around 62 and I want to include that in my answer, then I'm going to need to start at 61.5. Now, that's the area we're going to look for in our graphing calculator. We also need our mean and our standard deviation. Well, we know from binomial random variables that the mean is n times p from an earlier chapter. So that's 80 times 0.75. So that's going to be a 60 here for our mean. And then for our standard deviation, that's going to be the square root of n times p times 1 minus p. That's the square root of 80 times 0.75, and then 1 minus p is 0.25. And I get the square root of 15, which if I approximate that here, it's say 3.87. So now I have my mean and my standard deviation, 60, 3.87, and I want the probability that you're bigger than 61.5. So let's go ahead and put that into our calculator. So mean 60, standard deviation 3.87, and the x value bigger than 61.5. So we go into distribution, normal CDF for this. I want to start at 61.5. I want to go on forever, so essentially infinity. My mean is 60. My standard deviation is 3.87. I go ahead and hit enter, and I get 0.3492 if I round it there. 0.3492. And this then is going to be the probability that we are looking for. So, when you are given one of these problems, we're using the normal approximation of the binomial. You first do your continuity correction, figure out whether you're going to add or subtract the 0.5, and the best way to do that is from the picture. You need to figure out your mean and your standard deviation using the formulas from the earlier chapter. Mean is n times p. Sigma is the square root of n times p times 1 minus p. We throw that into our calculator. We learn how to calculate normal areas using the calculator, and we get our final answer to the problem.